van der Tak. I'm hosting this event on behalf of the Kaptein Astronomical Institute of the University of Groningen in collaboration with Studium Generale. Since not everybody may know what a Blauw lecture is, let me briefly explain. The University of Groningen initiated 6 visiting professorships to what is now the Faculty of Science and Engineering. And the Blauw lecture is one of these. It's named after Adriaan Blauw, a well-known Dutch astronomer. He's particularly famous for his work on high-velocity stars in the Milky Way and also on star formation in associations. He served many years as director of the Kaptein-Institute, actually, also as Director General of the European Southern Observatory and as president of the International Astronomical Union. After a gap of 2 years, it's a special pleasure, so that was due to the pandemic, it's a special pleasure for us at the Kaptein-Institute to welcome Professor Paola Caselli as the 24th Blauw professor. A few words about our speaker. Professor Caselli is director of the Center for Astrochemical Studies at the Max-Planck-Institute for Extraterrestrial Physics in Garching, and also an honorary professor at the Ludwig Maximilian University in Munich. Before this appointment, she was a researcher at the Osservatorio Astrofisico di Arcetri in Florence, a visiting scholar to the Department of Astronomy at Harvard University, and a professor at the School for Physics and Astronomy at the University of Leeds. As an astrochemist, Professor Caselli uses interstellar molecule to understand the formation of stars and planets and possibly the origin of life on those planets. It seems a bit ironic that although she is from a warm and sunny country herself, Italy, her research actually focuses on some of the coldest, darkest places in the universe, namely pre-stellar cores, and those are the places where interstellar gas and dust assemble to form new stars and planets. The conditions in those cores are quite extreme, such that normal molecules like carbon monoxide freeze out onto dust grains, which then gives rise to rather exotic chemistry with many weird ionized deuterium-bearing molecules such as H2D+. And then later, when a new star has formed, it warms up its surroundings and it leads to evaporation of organic material from those dust grain surfaces, in which we can observe with telescopes like ALMA. And Professor Caselli has worked on many aspects of this chemical evolution of the interstellar medium. And today we will hear from her about our astrochemical heritage, or how to make life out of stardust. We're looking forward to your lecture, and after the lecture, there is time to ask questions, and then there is time for drinks downstairs. Please, Paola, the floor is yours.
Thank you everybody for being here. It's a real pleasure to be here, and I really didn't want to stay up here, but it's the only way to communicate to somebody in the back who will be able to change the slides. Thank you so much for doing that. So first of all, I would like to thank the Kaptein Astronomical Institute that allow me to be here as a Blauw professor. This is a great honor for me, and I am super happy to be back. It was supposed to be 2 years ago, but actually I have been visiting Groningen for a long time. My daughter studied here, so I have a big bond with Groningen, so I'm very happy to be here. So what I will do today, I will take you onto a trip, and this trip is going from molecular clouds. These are the interstellar clouds, so the material that is in between the stars. Let's see if this is working. Yes, so this is the first step, and this is actually where the stars and planets are forming. We will go inside these clouds, and look at what Florence said, this is my preferred object, the prestellar core. This is really the beginning of stars and planets, so this cloud that become more and more concentrated, and then cold, and then finally everything becomes so dense that the photons cannot escape, so it warms up, and then finally you get your star there. Then when the star is born, we will see that things change quite a lot. The mother cloud will be dissipated away. These young stars are very turbulent, and they don't want to actually stay inside the cloud. So then you will start to see these beautiful disks. So there is the star with the disk, and this is where the planets are forming. And then, of course, we arrive at the exoplanet, and this reminds us a lot about our planet, which is the Earth. So what I will do, please, next slide, please. It's this type of outline. First of all, for you, I'm sure probably this is not needed, but I always like to start with this sense of scale, because it's very hard sometimes to understand these large distances. And so I will go through that, then interstellar clouds and the seeds of life, so these little molecules that we use to study the physics and the velocities, the motions of regions where stars are forming. Then I'll talk a little bit about the birth of stars, the assemblage of planets, and the origins of life, which is, of course, still a big question. So what you will hear my view on that. So be ready. Next slide, please. So we start from Groningen. So Groningen, you probably, I already forgot. I asked my daughter to tell me the name of the park, but I don't remember. So it's a Nordsen. Okay, fine. You know what it is. So we're here in Groningen, and this is about, say, 1 kilometer in size. We are all fine with that. And then we, if we change a slide, so we multiply here this number, 1 kilometer by 10,000. So now we go to 10,000 kilometers. Please, next slide. And here, more or less, we are not very precise this evening, more or less, we are at the size of the Earth. This is our planet Earth. Now, as you can see, this picture of the planet Earth is not so fantastic as we see sometimes in television and things and news, because this is the very first picture that was taken by Apollo 17 when they left our Earth to go to the moon. They had the sun on their back, and this was the very first picture that they could take for the whole globe. So I thought that was such an inspiration that I had to show you. Please go ahead. So now, 10,000 we multiply by 100, and we get to our sun. Can you click once more, please? Because there is now this little movie that shows our sun going around. This is, you can see now some, first of all, you see some granularity. It's not smooth and yellow as we see here. There are lots of things going on, and actually there are big flares that are coming out, but from the surface and dark spots. But this is what I want you to remember. 1 million kilometers. We are now at the size of our sun. Please, next. Now we multiply again by 100, and we go to the Earth-Sun distance. So now we are, you see, there are too many zeros, so I start to use these powers. And this is now 8 zeros, so we are at 10 to the 8, or 100 million kilometers. This is the distance from our Earth. I should also do it here. Okay. And then 10 to the 8 from the Earth to the sun. Now we multiply now by 100,000, because I don't want to stay here all night just telling you these numbers. And if I multiply by 100,000, now we go to, this is just impossible. So it's 10 to the 13, okay? 10 to the 13 kilometers. We are now at the edge of our solar system. So what is our solar system? What is the edge of our solar system? We don't even know precisely, because the edge of our solar system is made by these zillions of little bodies of rocks that are left over of the process of planet formation that have been scattered around through gravitational pushes and pulls. And now we are, you see the planets are just here in this little blue spot. And we have this cloud of icy bodies. Some of them sometimes feel the trigger, the gravitational pull, and they come here, and they are our comets. So I will show you actually in a zoom in of one of the most recent comets that we have studied. Now, if we go to the final 100,000, then you have our galaxy, which is the Milky Way, and this is the beautiful picture taken recently by Gaia. And one thing that you see, so please go on, because there are, yes, so here I put the size. So it takes 10 to the 5, or say 100,000 years, even for a photon, that's quite fast, to go from one side to the other of our galaxy. This is the whole size of our galaxy. One more click, please. And then here, because of course this is our view. We are sitting there. This is our home. We see this beautiful Milky Way, so these very bright patches that are just stars that we cannot individually recognize. They are too far away. But then the other thing, and this is what is at the heart, and my heart, are these dark lanes. These are the very cold, dark, because they are absorbing all these lights from the back, that they have stars in their back. They are absorbing it, and they are cold, and we will see, I mean, it's about minus 260 centigrades, really cold inside there. But these are the conditions that are needed to form the stars and planets. So for you to understand where we are in our galaxy, this is, of course, well known from a lot of studies from radio astronomy. And you can see here, so if somebody is watching us from above, we have our center, and we are here. It's about 26,000 light years away from the galactic center. And this is good because there is lots of activity here, and you don't want to be in the middle of this super activity. We're in a kind of quiet bubble at the moment. It's true, it's a real bubble, actually, that was, in fact, formed by supernovae some, say, 10 million years ago, so not even too long ago. And we are now sitting in this quiet region. So let's hope that it will keep like that for a long time. Please go ahead. So now, I wanted to show you a picture that you could take if you have the time and a good camera, because you need a quite good sensitive camera. So this, we are here in the States, and we are in a park, and you can actually see sometimes just with your naked eyes the Milky Way. It's just an amazing experience. And if you have a sensitive camera, then you start to see very well these dark lanes and all the stars that are in the back and in the front, mainly the ones that are in the front that are not extincted. So I wanted you to now see what Sir William Herschel said some time ago. And this is indeed when he was staring at the sky, and he built one of the most powerful telescopes in his time. He said, well, there really is a hole in the sky. At that time, of course, he didn't know what was happening in this dark region. And this was in 1785. We didn't understand that there was something in these holes, in this darkness, until the beginning of, say, so it was 1905, when, in fact, there was the first understanding that there was some kind of medium in there. Okay, so we can move on. And in fact, the dark lanes in the Milky Way are filled with gas and dust, and this is where stars and planets form. So if we look again at our Milky Way, now I will show you that instead of an optical telescope, we have a radio telescope, like even a small 1-meter telescope. This is, in fact, the next figure that is going to be on top. So you see that where it is dark, now it is bright. And this is 2.6 millimeter. This is the radiation that this very simple molecule that is the CO, carbon monoxide, that you know very well, is actually emitting when it is a little bit disturbed by the collisions of the most abundant molecules that unfortunately we cannot see at this temperature and densities, which is molecular hydrogen. Molecular hydrogen is the most abundant molecule in the whole universe, of course, because hydrogen is the most abundant element. But unfortunately, we cannot see it at this low temperature and densities. So this is a good, a good way to measure H2 from the CO, because the CO is very abundant. You can see everywhere there was a dark lane, there is in fact a CO. And we can actually make some estimates on the ratio between CO and H2 to measure the gas mass of these clouds. Okay, so then the conclusion here is that indeed the molecules and dust fill the holes. You will see in a few slides that CO is not the only molecule that fills the holes, and in fact this is the easiest to detect. So now to understand a little bit better about why astronomers need to use telescopes and even expensive satellites, we need to understand a little bit the electromagnetic spectrum. So again, here I will go relatively quickly. But the map that I just showed you, the map of the CO, is coming from this region here. So we are like in the radio regime, so 2.6 millimeters, so about in the middle here. So what you're seeing here is the wavelength, so the separation of these crests and draft. And the visible map that I show you of our Milky Way is in the middle here. And of course, we are very familiar with that. This is the size of, so the distance between these peaks is in a meter, is written here. And to give you an idea what I'm talking about, this is the picture of the objects or living beings, as I put it here, that have similar sizes. So in the microwave, we have, again, we are like in a familiar range. So here is grains of sugar. If you go to longer wavelength, we have meter size. So this is all familiar with us. But then in the infrared, when our atmosphere starts to become opaque, we need actually to go into space. And this is one of the most successful telescope in space, Herschel, that in fact is part of it has been built here in Groningen at the SRON, so we are all very proud. Can you just click, because I put yes here. It shows that, and in particular for me, this was the receiver with the high spectral resolution that allow me to look at this very cold region. But anyway, apart from me, there is then this decreasing of the wavelength to very, very short wavelength. So we go into bacteria here in the visible, molecules, atoms, and atomic nuclei. And here, again, we need the satellites because our atmosphere does not allow these photons to come through. Now, I wanted to insist on the millimeter because, again, these are telescopes that we use a lot for our cold clouds. So I want to show you the most powerful one in the next. If you can click twice, because again, here, there is a big contribution from SRON, because SRON has built receivers that allowed us to see different wavelengths in this large millimeter wavelength range, so different bands of ALMA. So this is the Atacama large millimeter and sub-millimeter array. This is at 5,000 meters, amazing experience. If you can go there, please go with some oxygen with you. But it's just amazing. And when I went there, I said, well, it seems to be on Mars, but then I realized I've never been to Mars, so how can I know how it is? But it's really looks like there is no life, but actually it's life everywhere, even there, okay? In these rocks, under the rocks, so you can see it everywhere. Okay, then the next one that I wanted to highlight, just as main instrumentation that now we are all very excited about, is JWST, so the James Webb Space Telescope that was launched on Christmas Day. That was during launch, I remember, I think my daughter can testify, while everybody was celebrating, I was, go, 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 go. And finally went, and I could enjoy my Christmas lunch the last year. And just to show you the amazing things that the James Webb is able to see, in the next slide, you can actually see the first picture of one of these molecular clouds that now we see the emission from the dust, and you see the edge. So it really feels to be there, because you have all these valley, mountains, and this very bright sky, just because there is no much material here. This is really the edge of the cloud. And inside this, so this is 7 times the size of the whole solar system. So it's really a huge place here, that just to give you again a sense of scale. And there are stars forming right now, and there are big stars, massive stars, that we will see they produce so very important elements, actually, for also life, that are now emitting very strong winds, and these winds are eating up and pushing this cloud away. Okay, so let me then enter into this astrochemistry business. So now this is an ugly table, and the reason why I put it on is just to show you, just to look at, not at the names of the molecules, but just look at how many there are there, and it's a lot. So I didn't even put all of them, because there are also what we call isotopologues. So actually, Florence mentioned there is, like, for example, the heavier cousin of hydrogen, which is deuterium, that I didn't even put, or the carbon-13, etc., oxygen-18, oxygen-17. Anyway, this is just the main molecules, and you can see that they can range from small molecules to atoms in size, like CO, but they can also go up to much larger molecules, and the majority of that are actually organic in nature. And this is no surprise, because carbon is the most versatile atom and can actually make a lot of molecules. And that's not by chance that, in fact, living beings, at least the ones that we know, are actually based on carbon chemistry. So one example is this amino acetonitrile that was detected in 2008 in a star-forming region, so in a region where stars are forming right now. And this is just one step away from glycine, which is the simplest amino acid. Now, glycine has not yet been detected in space, but we will see it has been detected in an object, like a comet, that maintain or keep almost unaltered the chemistry that is in space in these dense regions. So let's move on. And one question now that maybe you may have is how this molecule can form. You know, we are talking about very low temperature, which means very low energy. Things are moving very, very slowly around. And there is basically no energy. These molecules just want to sit in their ground state and do nothing, okay? Then what there is, there are some collision, as I mentioned. So H2 molecule collide with CO, and CO get a little bit excited, but then goes back in its ground state and stay there and float around. How do you make these big molecules in these regions? The densities are very low. It's not just the temperatures are low, also the densities are low. In our room, we are breathing now 10 to the 19, so you have to put 19 on top of the 10, molecules of nitrogen, and 2 molecules just breathing every time, in a cubic centimeter. In this region, you have at most, say, 100,000 in a cubic centimeter, but actually in the more larger cloud, we are talking about 1,000. So probability of colliding is really low, okay? So this is what we think is going on, and at least we know for some molecules that this is what is going on. These are the dust grains. These are the dust grains that are together with gas in this in this cloud, so that I have shown you. And they are, in fact, the grains that are absorbing this light from the background star, and this is the reason why these clouds look dark, because these grains absorb the UV light, they absorb visible light, and they re-emit in the infrared. And this is the picture that I show you of JWST. We are seeing this re-emission of the dust in this longer wavelength. It is fantastic. That gives you this idea of, say, how the material is distributed. But they are also very important because unlike in our atmosphere, where three-body reactions can actually allow molecules to form and react very quickly, because you have a third body that can take out the extra energy that is present when you actually form a new bond. You have a new bond, you have extra energy, and you have to release this extra energy, otherwise the molecule will just be destroyed again, okay? So in our atmosphere, there will be another N2 molecule that will just come and take this extra energy. In space, this doesn't work. And this is why we need these little dust grains, because dust grains are like catalytic surfaces. They are very big compared to the small atoms that jump on it. The small atom, like the hydrogen, they can go around very fast, and when they meet with each other, they form H2. And then we will see later on that actually you can form much more complex molecules. So this is what we need. Now, just to link to the origins of life, before just waiting until the very end, one thing that it's very important from my point of view to remember is that try to answer this question. So what is life made of? So if we look at the living beings like us, so we have 83 stable elements in our, periodic table. And but if we look at by weight, what are the most important ones? So 95% by weight, we are made out of hydrogen, oxygen, carbon, and nitrogen. If we ask what is our planet made of, and what are the most important elements, here what we see is that the four most abundant elements composing the Earth are silicon, iron, magnesium, and oxygen. So we are not made out of the material that our planet is made of. We are made of material that come from the stars, okay? So this is our composition is much more similar to my dark clouds than to this planet Earth, okay? So this is, I think it's very important to understand. And also this, I think it helps us to understand why there are all these molecules floating around in space. It is so easy for carbon chemistry to go on, as long as you have these small grains that take off the energy and make all these beautiful molecules. But anyway, so just a little glimpse on the origins of life. Let's move on. And here, you know, I'm talking about very important elements, so hydrogen, carbon, oxygen, nitrogen. You know that this is, say, the basic of all our prebiotic molecules. So, you know, RNA, DNA, most of it is actually made out of these atoms. But we also need other atoms. So we need, for example, iron. Our blood, we need to have iron. This is also calcium, and this is for our bones. And of course, we need these dust grains that make planets. We need something solid to walk on, at least as humans and also other living beings on Earth. So where these elements are made? Well, they are made inside stars, okay? And in particular, the heavier ones are made in the more massive stars. So some of our elements that we carry with us are actually coming from massive stars. Nothing to do with our sun. These are massive stars that have were born and then exploded billions of years before our sun, and then they enrich the medium of these atoms that then allow complex chemistry, if not life, to actually form in the universe. Okay, so we can move on now. And we arrive at my favorite, the dark prestellar core. So this is the prestellar core, that one of the prestellar cores that we see. And one thing that you notice, so there is a background here of very bright stars. This is, in fact, one of these prestellar cores that is close to the galactic center, so to the plane, is close to the plane of the galaxy, so there are lots of stars in the background, but in the visible, it's really dark. So we need to switch to longer wavelengths. I show you that millimeter is good, because this is where cold dust, for example, peaks, and we will see also many molecules peak at these wavelengths. So this is a millimeter continuum emission of one of our preferred prestellar cores. So one thing that you notice is that there is a very bright spot. This is, so look at the size scale here, is only a fraction of a light year, so it's a tiny thing. And here is where we know is going to form a future star and planets, okay? So when we look, last century, when we look at this with CO, what did you expect to see? Well, you expect to see something that peaks here, because the CO, as I said, is proportional to the H2 molecules, and then you should have a peak. But actually, the CO showed us a big hole again. So there is a hole in CO. How can we explain this? So the easiest way to explain this is that molecules in the very center of this prestellar cores, where the temperature are really low and the density is high enough to have enough collisions between gas and dust grains, these molecules, once they touch on the surface of these dust grains, they don't have the energy to go back, and they just stay there and rest on the surface of dust grains. So with the time, you have these little dust grains that actually become a kind of a snowball, and we will see this in the next. So molecules freeze out onto dust grains in the center prestellar cores. So you have your dust grains. So these dust grains are made of silicates, like our Earth. As I told you, these are building blocks of planets, okay? So you have silicates, some carbonaceous material, but these are hard carbon, more like graphite, than, say, carbon that we use in life. So if you just go next, just to visualize this, so we have, in the next click, we should see this typical grain. So this is actually an interplanetary dust particle that rains on us every day, tons of these interplanetary dust particles. These are made out of small grains. So in the center of this prestellar core, what happened is that they get all these molecules, and they get these thick, icy mantles on top of that, okay? So then we move on, and these icy mantles is not just, of course, CO. So we have oxygen, and oxygen, once it sits on the grain, it can be hydrogenated by this fast-moving hydrogen. And if you hydrogenate oxygen, you form water. You cannot go beyond water, because you don't have any more valence electrons, so you are actually done. So you have oxygen plus hydrogen, OH plus hydrogen, H2O, done. And this is a very, very quick thing. And we know that is there because we see, and now with JWST we see it even too much, these lines are saturated in absorption, so we have this, so lots of ice on top of this. And in 2012, when actually there was no JWST, but there was Herschel, we used the Herschel to actually detect water in the vapor. Now, this line, we cannot detect from here because even if H2O is not the most abundant component, just the few molecules that are in there are actually enough to make our sky totally opaque to the thermal emission of water coming from space. So we really had to go up. So this is what we saw. We saw this, doesn't even show, I mean, doesn't even look very pretty. I mean, it's really faint. Only with Herschel we were able to see it. We see emission, we see absorption. What is that? Well, this is actually a well-known profile that tells us that material is contracting. You see material coming toward you in the emission, and material that is actually going away from you at higher velocity in absorption. So we are seeing here water in the gas phase, and we also measure how much of this water there is. So in the next so this is good that this didn't start immediately, otherwise everybody was looking at the rotating molecule, but this is what we were seeing, rotating molecules. So with Herschel we measured 2,000, so in this prestellar core where one star will form and who knows how many planets and moons will form, we found 2,000 Earth's ocean of water vapor. We measured it, okay, thanks to this high sensitivity spectrum. And based on our models that include also the freeze out of molecules, etc., we know that if we have 2,000 Earth's ocean of water vapor, we have to have 3 million oceans. So this is about 2.6 Jupiter masses of water ice. And this is already there, and you have not yet even formed the protoplanetary disk and the planets. So you start forming the star and the planets already with this huge reservoir of water. It's all in there. And this is what we need to start models of, when in our community, say in astrophysics, we tend to have separate communities, but I always say that we always have to work together because we need to understand what are the initial conditions. You cannot start to form planets just starting with the disk. You need to start from the mother cloud, and this is what we have. So plenty of water for future moon and planets. Sorry, sometimes I get too excited, and maybe I shouldn't because we don't have enough time. Let's go ahead, thank you. So just to sum up here, just before stellar birth, in the central region of stellar cores, almost all elements heavier than helium. Okay, so hydrogen, deuterium, helium, they stay in the gas phase, they're light enough that they cannot actually freeze on the surface. But everything else is frozen. So we start with this, it's like a hailing. You have to think, this cascade, this waterfall of little hails that are just going toward the center and start to form the star and the protoplanetary disk. Of course, the material that will end up in the star will then evaporate, but some of this material will stay for the future generation of, say, the future steps that are going to be there. So formation of star and planets. So JWST, as I said, we are all waiting to look through these disks, early disks, and unfortunately, I cannot show much here tonight, but let's move on, because now, just to summarize this part, I wanted to show you this movie that, in fact, was done in the Netherlands, and Professor Evine van de Soek, she gave me the authorization to show it to you. You probably have seen it already, but if you can click it, then we start. It's a short movie. No, it should, please go back. It should have just one click to start. It takes a few seconds to start the movie. If you want to come there, maybe move a little bit the cursor. And, here it is. Thank you so much. So here we are in the interstellar cloud, and now we have to zoom in a lot, because the interstellar cloud is light years, and here is a fraction of a micron. These are crazy astronomers. So these are all the atoms. Red is oxygen, white is hydrogen. You see, we are now on the surface of this dust grain, and some of them actually combine. And wait. OK, so here we have O2. Now we have an hydrogen coming. Now another hydrogen. We are getting to Okay, and now you see you form two molecules of water, and this process, as I said, is really fast because you have a lot of hydrogen in the gas phase, and you will soon start to cover the whole dust grain with this beautiful ice surface, and it will continue to evolve and accrete more and more material as you go farther down in the center of these cold regions. Good. So this worked. Thanks a lot. So we can now move on into the what happened when you have a young star, baby star forming. So if you have an optical telescope, and this is Hubble, beautiful Hubble, you see nothing. You see basically dark. This is where the young star is. The young star is surrounded by a cocoon full of dust. And so you really need to go into the infrared. But what you can see with Hubble are these beautiful, we call them outflows. So the material that is actually going away outside the cloud, you now start to see it because this is hot stuff, and you have material that is emitting in the visible or in the near infrared, and this is the energetic winds. So the young star already wants to punch away the mother cloud and get liberated by all this material around. So if you just click again, now this is an artistic impression. So if we had the perfect telescope that allow us to go inside, and actually we have, in fact, ALMA is not so very far from this, you can actually see what's happening. You have already the formation of this disk. This is the protoplanetary disk, the young disk where the planets will form. And then there is this wind. The wind cannot actually go isotropically. It has to go perpendicular to the disk. And this is why we have this bipolar, we call it bipolar jets, that make true holes into the cloud. And so in the next, we now go closer in. And now here is actually a real picture. This is coming from ALMA. So in the very early phases, this is just to let you know, this is the youngest protoplanetary disk that we have at the moment with such a level of detail. So this is something like 100,000 years old, a little bit more. We are billions of years old, so just put this in prospect, no? So we see already, at this very early stage, we see evidence of some rings and gaps. And these ring and gaps, what we think is going on is that the materials start to assemble at certain orbits around the star, and in this region is where you actually will planet form. So we start to see this kind of condensation of material. And the next is actually a slightly older disk, very famous. This was, in fact, if you click again, there is, yes, in 2014, this was the first image of this HL Tau, which is in Taurus, is not too far away from us. And you see here, sorry, just in the next one. Yes, so here you see now very well these gaps. And what we think is going on is where you see these gaps is really where the planet, or the young planet, is orbiting around and eating up the material in this region. Again, this is done all with ALMA. Thank you. OK, so assemblage of planets. So what happens here? Now, this is a huge problem because there are still things to work out, because we don't really know how to go from these sub-micrometer size grains that are present everywhere in molecular clouds to planets. It's big, again, it's orders of magnitude change, no? So you have to put things together. Of course, having ice helps. You can start to make some little pebbles, but then the pebbles have to actually become planetesimal, and the planetesimal can have to become planets. And then, of course, there is the question if you want to make terrestrial planets, if you want to make giant planet. In the case of the giant planet, you need actually to have what we think is going on is if it is formed in a protoplanetary disk like this, you have to form the massive planets a little bit farther out where the water and these volatiles are actually in ice form, so you increase the amount of solid material that can make the core of your planet, and then the planet will just gather all the gas. But I'm not going into the planet formation because I wanted to focus on the origins of life. So please, let's go next. So this is just another artistic view to show you that with the time, the dust to gas mass ratio increases. So you have more and more dust, less and less gas in your disk. So you are left with this, what we say sometimes scrambles, but these are pebbles that are actually participating to the formation of the planet. So once you have the planet form, you keep accreting this material that can come from, say, the outer part of the solar system, in our case, or nearby, for example, in the asteroid belt, you have also a lot of collisions between asteroids, and you can actually accrete pieces of these asteroids. So this is also a very important part that we need to keep in mind, because once you form these planets, when they are very young, they typically are also very hot. So even if you bring with you a lot of organic molecules, maybe many of them are actually lost because of the heat of formation. Again, here, this is a different type of heat, because this is coming from the gravitational contractions. So this is energy from the gravity, and also from, say, radioactive nuclei that they last, say, for a long time to maintain the rocks warm. You need this extra, say, bombardment of material that could actually bring volatile. So is this the case? The question mark. So this is a picture, again, an artistic view of our Earth with the moon very close, because you know that when the moon formed, this was about, say, 4.2 billion years ago. There was this giant impact of our Earth with the Mars-sized planet that actually formed the moon. You can imagine that this event was so violent, so destructive, that definitely, again, even if there was some time after the formation of the Earth to make something that even resembled vaguely the life, it was destroyed. So if you can click here, I just wanted to tell you what we know about life in our planet. We know that it exists since about 3 billion years ago, and this is because we have these fossilized microorganisms in rocks, but these are already very much evolved, okay? So there must have been something before that followed, say, this amazing transformation from inanimate to alive. Okay, sometimes, you know, I keep thinking about that. It seems, sometimes it really feels like there is a little change, but there is this change from inanimate to alive, and we can debate the whole night about this, what is alive and what is not alive. Unfortunately, we cannot go back farther than these 3 billion years, because our Earth is also apparently alive. We have these tectonic plates, and it is moving, and it is dragging down this surface where the first living organisms were formed. So this is lost to view. So let's go back then now to the fact that when our planet Earth formed soon after the collision with another planet that actually formed the moon, so it was really like a magma everywhere on our planet, so the Earth started to cool down. And at that time, you have this continued bombardment from these building blocks of planets. Part of them could be these comets, so coming from the outer part of the solar system, bringing lots of volatile and water, but also meteoritic material, so objects that have been forming closer to the Earth could have brought some more volatiles. What do we know about this? Well, for example, you have seen, I'm sure, this beautiful picture of the comet 67P, that have been visited by Rosetta, and we know that these contain building blocks of prebiotic molecules. This is the picture that ESA, so this is not a joke, this is a very serious slide that shows when actually the Rosina team, so this is one of the instruments on board of Rosetta that were supposed to measure the composition of the comet, they were totally astonished, no? So they found all kinds of molecules, and they didn't know how to list it. I think just for fun, they made this cometary zoo. And of course, I'm not going to read them all. You can actually read some of them, but you see that they have all kinds of molecules that are in fact also present in space, first of all. And the second thing is that they have this, in fact, the king of the zoo, which is glycine. They found glycine, the simplest amino acid, is there, okay? But then you also have all kinds of sulfur-bearing, iron, potassium, silicon, all kinds of things that, in fact, are just needed to make things more complex. So let's go to the carbonaceous chondrites. These are the primitive material in our solar system that, in fact, are part of the meteoritic material. So this is coming from the asteroid belt. And some of them, so this, in fact, the carbonaceous material, carbonaceous chondrites, they have this interesting composition where you have dark, which is the matrix, and then other, say, sometimes chondrules, sometimes other like little dust grains. So it really looks like you have this compaction of dust grains. And then something must have happened. Something must have cooked them up. And what it is that? I mean, this is the sun, of course, that in fact some of them have been close enough to the sun to reach a temperature of a few hundred Kelvin. And this could probably allow chemistry to go on. But what do we find inside? This is the amazing thing. So if you look in this primitive material, this is some of the oldest rocks in our solar system. They have been formed much before our Earth, okay? Now, you find everything you need. You find even more amino acids that are needed for us humans. We use 20, and this is used by all living beings on Earth. No, they have even more than 200 in some of these have been found. You have all kinds of bases in RNA and DNA, so adenine, cytosine, guanine, thymine, uracil. They all have been found there, okay? And also ribose, that is, of course, important for the backbone of our, for the RNA. And they have been identified. And so here I just put some of the amino acids that have been found. So this is my view of the world. So my view of the world is that in these carbonaceous chondrites is really like you have all ingredients that you need to form something complex. And of course, whatever it is that is complex, the shape, the form of this complexity will depend on where these rocks will land. So those that landed on Earth, early Earth, they found conditions that actually allowed on the Earth to form us. And in the next slide, in fact, I wanted to start now this little discussion. So if you just click one more time, so we have the DNA also. So here we have the RNA molecule, the DNA. So the big question, once you have the Lego box, you then have to know what to do with that and how you bring up from this mess of little pieces, color pieces, you have something that actually makes sense, at least for us. So how to assemble these components into much larger molecule, or say how to get molecules to join together in a repetitive fashion like our, say, main constituents, like genetic code, for example. Well, the answer is that nobody really knows. In fact, and no one has been able to generate RNA or DNA spontaneously in the lab. This is where we bounce our head every day, because not actually me, because this is mostly for the our colleagues biophysicists, but we are very supportive because we really want to know, okay? So we don't want them to bounce their head so often because it's really tough. However, in the next slide, there are, I mean, this is just one, but there are many interesting ideas, and of course things are moving on very fast, so hopefully one day we will know. One thing is, for example, clays, that of course clays are everywhere in our planets, and their structure is such that can actually concentrate organic molecules in their layers. Actually, if you click once more, there is the structure in electronic microscope that you see that you have layers made out of silicates, then you have some aluminum, and it can actually concentrate the ionic forms like NH4+ and other ions that can actually be structured and organized in a way that can make repetitive structure. And one thing that clay are very good in doing is to absorb the water, because this is what you need to do. You have to basically react a component here, formed on one end with OH, to oxygen and hydrogen, and then here with the nitrogen and the hydrogen. And to make an amino acid, so this is a carboxylic acid, and this is the amine part. You have put these together and form water. So water has to go somewhere. And clays are able to absorb this water. So in the next slide, I can now show from the theory. Theoreticians are much more optimistic. And it's interesting to see the debate between theoreticians and experimentalists, because theoreticians say, this is all wrong, it cannot be true, because in my lab I cannot do it. And the theoreticians say, well, you're doing something wrong in your lab. I mean, so it's all like this, it's just, yeah, it's a lot of fun. So anyway, this is what Pierce et al. Have written in 2017, 2022. So they reproduce in their head the conditions of the early Earth, and then assume that you have this delivery of primitive material. And then, considering all the ingredients that they have, that we know very well, they can actually start to look at what happened when you have the dry and wet cycle. You can have precipitation. You have a very fast rotation. Remember that our Earth was rotating, so the day cycle was only a few hours after the moon was formed, okay? It was really, really fast. So you have day and night, very fast, lots of tides, lots of, material still accreting. So the conditions must have been really accelerated. And then they could actually make RNA from these building blocks that we have seen in meteoritic material only 200 million years after the moon forming impact. So this is what we are doing in Munich, but also here in the Netherlands, because in fact in the next click, there will be the Origin Center that is actually a great assembly of, it's big actually. The Origin Center is much bigger actually than our Origins cluster, because it, I think, includes more than, 300 people, more or less, in the Netherlands. And there are lots of connections also with the rest of Europe, Germany, and collaborations. So I'm actually very excited about this. And hopefully, I have to understand how the life form before I retire. Is that possible? Okay, well, let's see. So let's move on. We are getting to the end, actually, because now I just, this statement, that a few more statements. Oh, it's late. Should I cut? Or cut. Okay, fine. So, but this is going to be fast. So one thing that, again, I want you to remember, take home, is that on our planet, life is everywhere. You can even take some of these bacteria, or even not bacteria, even like extremophiles, take them in the, say, space station, and actually take them there for hundreds of days, they don't die, okay? The life is tenacious. And it's everywhere. It completely permeates the surface layer of the planet. We find beneath the deepest ocean, the highest mountain, as I told you, at 5,000 meters. Yes, there is life, and not just astronomers. I mean, and the highest mountain, the driest desert, coolest glaciers, deep down in the crust of rocks and sediments. So, this is my summary, but after this, maybe we can just stop here, I guess. I just had a couple of sentences that for me are very inspirational, but we can first discuss, and if there is a time, we can go into the inspiration. So I wanted to remember from tonight that stars with their orbiting protoplanetary disks are producing interstellar clouds. And these clouds are already very rich in organic species. These are the building blocks of these bigger prebiotic molecules. Planets are assembled in protoplanetary disks from dust, ice, and gas that are originally part of the cloud. And can you just click on just one more, because I wanted you to remember, visualize this. Then in disks, icy dust grains stick together, forming pebbles and planetesimal building blocks of planets. If you can just click. So this is a little picture of Ryugu, is one of the asteroids where the Hayabusa 2 landed. And we can see, indeed, that this is a rubble pile, not pie. And this is actually, is hungry. So this is a lot of little rocks that are assembled together. And this is the idea that we have, say, of planet formations, so putting together pebbles. Star hits the pebble, planetesimal, and then active chemistry occurs in the interior. So prebiotic molecules emerge, like amino acids, but also nucleic acids, etc. Interstellar dust and rocks continue to rain on planets once formed, bringing prebiotic molecules ready to be assembled. And this is just for you to visualize, is this comet that is actually coming down. And this will fortunately happen in the past, but it's not very likely now. Astronomers, chemists, and this is very important for us scientists, that we need to work together. So it's not just astronomers, it's also chemists. In fact, this is where astrochemistry, in a sense, comes from. But we still need to talk to the expert. So in this case, chemists, physicists, geochemists, and biologists to actually unveil our astrochemical origins. But as you can see, it's really a lot of fun. So please, go ahead and look for more material. It's just what we need in these days. Yes, to keep up.
Many thanks, Professor Caselli, for taking us on this trip and telling us about our journey, the journey of our astrochemical heritage. We now have time for a few questions. If you have a question, please raise your hand and wait until somebody gives you a microphone. Who has a question? All the way in the back.
Hi, good evening. Thank you very much, Professor Caselli. It's
you.
a wonderful talk. It's really eye-broadening. This confirms my idea of astronomy and astrophysics. It's a study of extremes, extremely large, 10 to the powers of 30, so large. And it's also a study of extremely small, down to the molecular level. I'm not so 100% sure about the life, but I want to ask about the life of the star, because in our solar system, we have only one star, our sun, but also in other solar systems, you have like 2 stars, or I'm not sure whether we have 3 stars systems. So how do you know when the star began forming, whether you will have one sun or a twin or quadruplet? So that's the question about the stars. And yeah, thank you.
Yeah, that's actually a very good question because, in fact, they say at least 50%, if not more, of the stars are binaries. And some of them, in fact, are triples. And we also have these massive clusters with lots of stars around. So we know so I don't know if now I'm saying exactly what you want, but otherwise you tell me again. But so we know that the stars are forming in binaries when we actually observe, for example, also with the ALMA. So when we go deep inside the cocoon where the star is forming, we are able to see if there is one or more peaks that actually are the location of the young stars that are forming. And in many of those, indeed, we see the presence of more than one. And it's actually very beautiful because, in this case, you have your disk, the protoplanetary disk, and inside the disk, so we call it the circumbinary disk because it encloses both protostars. And the two binaries are actually fed by the circumbinary disk by structures. They look like some tubes. I mean, this is really not the right, but they're like some funnel flows, more technically speaking, so a little connection to the circumbinary. And you see material, actually, that is transported down to each of these two binaries. And it's, so what is happening there, within this region where you have the binaries, there is not much chance, from what we see, to form planets, for example, but you can form planets in the circumbinary disk if there is enough material. So I would expect there to see planets in wide orbits that may be a bit cold, the icy world or something like that, but these are very early stages, what we see. So what happened with the dynamical evolution, who knows? I mean, it could also be that some planets are actually migrating inward and started to orbit one of the stars. And this is, and I think Kepler, when there are actually examples of stellar systems where you have planets orbiting binary stars. So they exist, they can form. If there is life there, nobody knows.
Thank you. Who has another question? Yeah?
I was just wondering, the ice grains, or the grains are really important, or the dust grains, but where did they come from?
Right, yes.
Like, why aren't they broken up all the time? Because they seem to persist and they're there without much effort.
Right, yeah, that's another very good question. So dust grains, at least in our galaxy, we believe that they are formed in the atmospheres of evolved stars. So these are they are called AGB, so asymptotic giant branch stars. And in their atmosphere, there are the right conditions where you start to make the seeds, the first seeds of these dust grains, and then you coagulate with the very heavy species elements like titanium oxide, and then you start to actually grow around the silicates, and then maybe also carbonaceous material, depending on if the star is actually oxygen-rich or carbon-rich, you can make silicates or oxygen. But you're totally right. Once these dust grains are actually expelled, because during the last stages of the life of these stars, the atmosphere is actually expelled returned into the interstellar medium. There are, of course, they go through shocks, because there are, supernovae shocks, or there is harsh radiation that some of this carbonaceous material can be, say, destroyed. They can shatter. They can be destroyed. So it's actually a big question to understand if these dust grains can actually regrow within the interstellar medium. And this is something that there is a bit of debate, but at the moment, let's say that at least in our galaxy, the rate of formation is with the AGB stars and destruction through shocks is working quite well. It starts to be a problem in the early universe, in fact, where we see a lot of dust and we don't really know how that can be made and survive. So still a lot of, say, a lot of research going on in that direction.
Mm-hmm. Yes?
So with this image from the James Webb Space Telescope, you said that the clear delineation between, we'll say, the red-pink part and the blue part is from solar winds. Is that correct?
Yes.
Okay. So do we understand how the dynamic of those solar winds works to really maintain such a clean cut in terms of what we're seeing there and to sort of sustain the delineation between those two areas, since it looks very, very clear?
Right, right, yeah, it's just almost unbelievable, is it?
Yeah.
Yes, no, so there are, of course, lots of studies on how these, say, stellar winds are also from a massive star propagate in the medium. So what happened, and I think this is what happened in here, is the wind, instead of destroying, is actually pushing. It's like, you know, when you try to get rid of the dust, and you're just accumulating instead of destroying. It'd be great if we can destroy everything. No, we accumulate in some. So this is what happened. It's just pushing the material, and it becomes denser and denser at the edge. And in fact, in some regions, we see that, not probably here, this is probably not too massive, but sometimes we see new stars formed just at this crest, because it is pushed too much that basically you are allowing the material, the gas there, to collapse and form a second generation of star. So it's a plow. I don't know if this is the right word in English, is it? Yes, okay, thank you. Eventually it will be evaporated though, you know, with the time, yes.
Yes?
I had a very quick question about the solar winds, because I don't really understand that, how they can be created, because I thought that in space there was nothing else but empty space, and that wind and like noise is not really possible there.
Right. I'm afraid I missed the subject. What is the thing that you don't understand?
How solar winds are created, or how maybe like the solar star can create those winds. Because I thought there was no other medium than just empty space.
Oh, no, yeah, yes. So it is empty from the point of view of, say, when you compare to, say, as I said, our room, it's really like an ultra vacuum, no? But it's not, definitely it's not empty. And you have, say, plasma everywhere. And you have, of course, as I show you, in the early phases where the young star is still embedded, you have winds in forms of bipolar outflows. When you have basically clear up all your material around, you start to have more isotropic winds. And this is just like our sun. I mean, our sun is also, it's famous for having a strong wind that in fact propagates particles, like also protons, accelerate particles, and it just goes all the way to the edge, say, of our planet. You know, if you know, maybe you have heard about the Voyager mission, that in fact now is now just outside the edge of our, say, solar wind edge, in a sense. So this is what happens. It just propagates because it has so much energy. You have, of course, photons going out, and you can think of light particles also being ejected away. It's a way of cooling, of releasing all the energy of the star. So don't think of an empty space. It's not even intergalactic medium is empty. There are still some atoms and ions there that fill the gaps.
Great.
There is one more question. I don't know.
Okay, one quick last question.
Ooh,
Thank you for your very interesting talk.
thank you.
Your enthusiasm is also very inspiring. My question is, so we now live in the age with the James Webb Space Telescope starting. Is there a discovery that you are maybe hoping for or looking forward in the coming years?
Aha, with the James Webb. I want to see, I really want to see go through the very center of this prestellar course that no other telescope I have been able to do, because everything that is behind is just too faint, you know? So I want to see through and measure the composition of the ice that is in this very center, because these are the, you know, in a sense, I think I know because I have models. So my models tells me that there are this molecule, this molecule, this molecule. I want to test my models. So this is the thing that I really want to do. And of course, the next will be to see through a protoplanetary disk and see how much similarities there are between the prestellar core and the disk in the mid plane. So yeah, waiting for it.
Thank you.
Thank you.
We all wish you good luck with, with that. Let's thank Professor Caselli again.
Thank you. I want to thank my assistant down there. Thank you so much for your patience.
And I also would like to thank you. And in fact, I have 2 presents for you. The first is from, yeah, maybe. Yeah. Yeah. The first is from the Kaptein Astrochemical Institute, and it is a biography of Kaptein himself. Yeah, written by one of our professors, Piet van der Kuit.
Perfect. I love biography. Thank you so much.
Yeah. And the other present is on behalf of Studium Generale. It's a novel by a Dutch writer, Harry Mulisch. It's called The Discovery of Heaven. It's very appropriate. Part of it plays at the Westerbork radio telescope.
Okay.
I personally like it myself because of one of the characters in the book is called Florence. So.
Okay.
Thank you again for your lecture. Enjoy the reading. And
Yes.
Everybody now is invited for drinks downstairs. I'm told that there is a little survey and a QR code about that, but I don't know the details. Maybe somebody else can tell us.
Yeah, so I'm Yul Janing, and I'm a student assistant at Studium Generale. Right now I'm also conducting a small research there. There should be a QR code on the screen right now, but there isn't. So I'm going to send you an email with the survey, and it would help me a lot if you could fill that out later this week. So thank you. Have a nice evening.